Good morning, everybody. It's an enormous privilege to be here, to see so many people in the room. You all know what Rosetta was last year. Hopefully you all saw it on the TV and watched it online, but I'm here to give you a bit of director's cut today, a little bit of background in some of the things that we did to help you share in the adventure, and also to explain to you why we did it in the first place. So, I'm going to see if we can actually get some, there we go. So comets, why comets? What are exciting about comets? Well, comets are these objects that appear in the night sky semi-randomly, it seems, and not so often that you get bored of them, but not so infrequently that you'll never see one in your lifetime. This is a comet seen in the southern hemisphere a few years ago. We're long overdue a bright comet in the northern hemisphere, so everybody in this room, look forward to that. It will happen. We won't know when. Largely, these things are unpredictable, but some comets do come on a routine basis because they're in a nearby orbit around the sun, and that's the kind of comet we went to go and catch recently. So what is it that's special about comets? Why would you, they look pretty, they look beautiful, why would you want to go and see one? They're leftovers from the birth of the solar system. If you like, they're the dust left under the bed when you made the bedroom, and if you can go and investigate the dust under the bed, you might be actually able to work out how the people built your bedroom, if you take that picture. So when the solar system was built, it was built out of a cloud of gas and dust and ice and other materials. Some of that ended up in the sun, a very hot body. Some of that ended up in the planets. A lot of it was left over, and those are left over in the inner solar system in asteroids, rocky objects, in the outer solar system in comets, which are roughly 50% dust and 50% ices, water, carbon dioxide, carbon monoxide. Why is that interesting, studying the dust? Well, when the Earth was very young, it's very likely that the Earth was very hot, and there will have been no liquid water on the surface. So where did the water that's in this room, and the bottles of water I see under the seats here, in you, where did it come from? It was probably delivered to the Earth a few 100 million years after the Earth cooled down, 4.6 billion years ago, and so you could actually be that material. That water came from somewhere on the outside. And if we go and look at comets, maybe comets, because they have a lot of water in them, maybe they brought the water to the Earth that we are today. But even more than that, comets are loaded with complex organic molecules, things made of carbon, hydrogen, oxygen, nitrogen, the stuff that we're made of, the stuff that life is made of. And comets have that on their surfaces. They don't have bugs, they don't have bacteria, they're not life themselves, but they have the building blocks of life on them. And if that material was delivered to the Earth in crashes onto the surface billions of years ago, maybe we are all comet stuff. So that's why we want to go and study these things, to find out about our origins in the solar system. Now, in 1986, one of the most famous comets of all came back to Earth on its 76-year journey, and that's Comet Halley. And we were in the space age then, so we were ready with one of the first missions to go and study a comet close up. And this is the European Space Agency's Giotto. And Giotto did something completely unique at the time. It flew past the comet as the comet flew through the inner solar system. But it could only just do that because the comet was moving so quickly, we couldn't actually rendezvous with it. It's just like the way that you would want to, if you had Usain Bolt running from one end of the room to the other, and you wanted a conversation with him, there's no way. I can guarantee there is not one person in the room that would keep up with him if he was serious about the run, okay? But you could have a very short conversation with him if you stood at the 50-meter line, and as he was running past, jump out and go, hop! You'd get half a syllable out as he ran past. And that's what we did in 1986. We actually flew past Comet Halley at a speed of 68 kilometers per second. Pretty fast. So we had just seconds, up to a minute, of this close encounter as we flew past this amazing object. So we learned a lot because nobody ever done this before, but at that time, people already knew they wanted to go to the next stage. They wanted to be able to rendezvous with a comet, get up close, fly alongside it, and watch it as it came into the inner solar system and burst into life, as comets do. As they get hot, the water sublimes from the surface and flies out into space and creates the tail. So to do that, we built this machine. This is Rosetta. It's a huge spacecraft. It has solar panels which extend 32 meters across. That's the size, the wingspan of an Airbus A320. The spacecraft itself is at the end. It's a 3-meter cube weighing 3 tons. Seen up close from underneath, there it is. Half of that is propellant to maneuver around the comet. And on the side there, the box poking out the side with all of its covers on is the famous Philae, the lander that went down to the surface. Philae weighs about 100 kilos. Rosetta is the big science machine. It has all the big science instruments on it, the big cameras and the mass spectrometers and all the things we do science with. Philae also has those miniaturized to go down to the surface. So this was started in the 1980s. The building started in the 1990s. And in 2004, we were ready to launch it. I work in space, so I have to show you a launch. So that's what we do in space. We build incredibly expensive, incredibly sensitive, delicate hardware, and then we shake the crap out of it for 7 minutes. And if it survives that, then we can do some science. So off we went in 2004 from French Guiana, from our launch site in Kourou on an Ariane 5. And where were we going? We were going to this object called 67P, and that means the 67th periodic comet ever discovered, and was named for the 2 Ukrainian astronomers who had discovered it some years earlier, Churyumov-Gerasimenko. For us, 67P, okay? So 67P goes around the sun every 6.5 years. It goes out beyond the orbit of Jupiter and comes in between the orbit of Mars and the Earth. It doesn't go super close to the sun, but there's a big range in distance, so a big range in activity. As the sun's heat builds up, the comet bursts to life every 6.5 years. So, with Giotto, we could only manage this quick Usain Bolt half a syllable on the 50-meter line. How did we actually get to rendezvous? Well, you're all young, so you're going to be able to take this video and really quickly. 10 years in 15 seconds. This is what we did to get there. So we launched in 2004. 1 year later, we came back to the Earth. We used the Earth to fling us faster into space. We did the same at Mars. We came back to the Earth again. We went past an asteroid. We came to the Earth again. We went past another asteroid. And by that time, we were on the right trajectory to encounter the comet in 2014, do the rendezvous, drop the lander, get close to the sun. That's the whole mission in 15 seconds. So it took us 10 years to do these crazy flybys, coming super close to the Earth and Mars, so that they have acted as effectively a rubber band to fling us into space faster than we were before. So that's why it took so long, because you can't just do that in a weekend. It takes you a while to get around the solar system. What we did in 2011 was very interesting. We were so far from the sun, even with these huge solar panels, we didn't have quite enough power to run the spacecraft safely, so we turned it off. We put it into hibernation, we turned all the guidance systems off, we turned all the computers off, we span the satellite up once a minute so that it would stay stable, orienting its panels at the sun so that we had enough trickle of power to run an alarm clock. And we set that alarm clock for 2 years and 7 months in the future, and we waited until the satellite came closer to the sun again. We got enough power to be able to operate safely. And the alarm clock, we waited for it on January the 20th. We waited, and we waited. Beforehand, we had flown past the Earth. We could wait, look at those pictures. Yes, we went to the Earth once. We even went to Mars once. We did that as well, but we were waiting for the signal. And he got pretty nervous and anxious there in the control room. This is 18 minutes after the signal was due to come. These are the people who've worked their entire life on this mission. If it didn't wake up, we did not have a mission. So there was a sweepstakes in the room that day, and this is the moment that the last person's bet on the time went past. Luckily, 18 minutes late, we got signals to the big ground stations in the southern hemisphere, and 1 minute later, that was the reaction. So it was a huge moment, January the 20th, 2014, because we were ready. We could now go and explore this amazing comet. This is what we saw in May last year as we came close to the comet. This is from the spacecraft. We see it turn into a comet. We got it right. We're not going to an asteroid. We are going to a comet. As we got close, things got a bit strange because we saw this rather weirdly shaped object which was christened the rubber duck at the time. Looks like two pieces. And in fact, scientists were really excited at this time because they thought perhaps we had two comets for the price of one, two that had bumped together. The engineers hated this because they had to fly around this object. And this doesn't have uniform gravity, an object like this. So scientists and engineers, we get on very well, but different attitudes to different problems quite often. And as we got even closer, this is a crazy object that we ended up at. This is 4 kilometers across. It looks like solid rock. It isn't. It's mostly porous. We now know that by sending signals through the comet. We know it's 80% empty space. Not caves, not enormous hollow. It's not an alien structure. It's just a fluffy ball of ice on the inside with a crust on the outside that's been affected by the sunlight every time it's been around the sun, every 6.5 years. And here's the key thing. When we saw these pictures, we knew we had to land on this. And we knew the precision with which we could land was to within 1 kilometer on a 4-kilometer wide object. So this was obviously going to be a challenge with a surface as rugged and as rough as this. So when you look in more detail, you see these kind of almost geological landscapes. You see cliffs, you see boulders, you see ravines, but you have to wipe all of that thought from your head because this is not the Earth. There's not much gravity here. It's incredibly cold. It's not rock. Everything you're seeing here is a mixture of ice and dust and quite loose. So when you try to understand how this came about, you really have to stop thinking about the holiday you had in Arizona with those lovely mountains and think about how does an object like this actually behave? You see these enormously wonderful vistas with things that look like boulders, and these boulders are up to 20 meters high. How did they get there? Where have they rolled from? Maybe, in fact, what happened was that they lifted off the surface during a previous episode, never quite achieved escape velocity, and fell back down to the surface somewhere else. And indeed, if you look at this picture, just to give you a sense of scale, the biggest boulder in this picture down in the bottom right, we called Cheops, after the large pyramid in Egypt. So I thought when we had this picture, I wanted to put it to scale. So I went into Photoshop and did this, and then immediately realized that the European Space Agency could not release this picture online. So I arranged with a journalist friend to release it anonymously on the BBC. But now I can out myself. I did make this picture. It's just to scale, that's all it is. But we have got some people out there who do think this is an alien spacecraft that we've rendezvoused with. Now, so this is what the comet looks like. And I told you before, scientists are really excited about whether this was actually two things that had come together, or is it one object that's highly eroded. In the last 2 weeks, papers have been published. We now understand that this is actually two comets that came together. We can look at the structure of the surface. We can look at how all of the planes of the terraces on the surfaces are oriented with their gravity. And we know that something like this must have happened 4.5 billion years ago. This whole movie only takes 60 hours. This is a very quick process. Two objects in the outer solar system encounter each other at a few meters a second and end up with something that looks a bit like our comet. So we know it's two that come together. So now it's exciting. Can we study both halves and learn more about perhaps two different comets out in the early solar system? Now, we get to this point again where we look at things like this and you have to say, look, stop trying to understand it the way you understand it on Earth. Because when you look at this picture, looking from the small head down to the large body, you look at it and you ask one question. Look at where the boulders are. On the near side and on the more distant side. And in both cases, ask yourself, where is down in that picture? Because it's a small object and it's very rugged, and down is actually where gravity pulls you, however low the gravity is. But that gravity changes continuously across the surface, and there are places where you can be 500 meters from somebody else, and their gravity is at 90 degrees to your gravity, as you see in these boulders here. What I'm going to do here, so you'll all get a bit tactile, is I'm going to hand out one to each group here, models of the comet. You can get to feel it, and it's a small-scale model, of course, but there is one feature about it which is very important, and I'll tell you about that in a second. So, talking about gravity, the gravity on this object is very low, but it's not zero. We do orbit around the comet. So this is one of my favorite pictures. This shows a close-up on the surface of the comet, and it shows a cliff which is about 100 meters high. So everybody in this room, it's a young audience, I can guarantee everybody in this room is thinking, base jumping, right? What would it be like to base jump on a comet? Well, you know, it would be the most boring base jump in history, because to get from the top of the comet to the cliff to the base, 100 meters, would take you 20 minutes. Now, your parachute wouldn't work, there's no atmosphere, but you don't mind, you don't care, because you reach the surface at 25 centimeters a second, which is this speed. So you just walk off the bottom of the base jump. But, this is the key thing. You know about base jumping, right? You've seen videos. If you haven't done it yourself, anybody done base jumping? I haven't encountered an audience where anybody's done it yet, but somebody will one day say, no, that's not how base jumping is. The one thing you have to do when base jumping is be careful you don't hit the stuff immediately beneath you, right? So what do? You stand at the top of the cliff, and you push up and you jump, right? You might have a problem on this comet because the gravity is only 100,000th of the gravity on the Earth, and if you reach a speed in that first jump of 0.9 meters per second, 90 centimeters a second, you have reached escape velocity, and you will fly off the comet. So that's pretty easy to do. All human beings can do this, so if I ask you all to stand up, because I'm going to teach you how to jump off a comet now, because to reach 90 centimeters a second, you only have to be able to jump 4 centimeters high. So pretty much everybody can do that, so I'm going to get you all to jump 4 centimeters on my count, because then the cameras can capture it. We're going to jump off a comet. 3, 2, 1, go! Well done. You have reached escape velocity from 67p. Now, here's another extreme sport on the comet. I didn't make this one, I can assure you, but it's kind of cool. But it illustrates an illusion. Every picture you've seen so far, the comet looks nice and white, nice and fluffy. It looks like snow. It's not like that at all. I told you about the comet models. The comet is actually jet black. So this is the comet. I've lightened it up so you can see it. I'm now going to drop it down to the real brightness of the comet. It reflects only 6% of the light that falls on it. It is dark. If you were in a coal cellar, it is as dark as a coal cellar. Nobody has coal cellars anymore, I suppose, but it is that dark, okay? Now, all the pictures I've shown you as well have been black and white, and you're dying to see the comet in color as well, okay? So I'm now going to turn the brightness back up. I'm going to turn the color on, okay? Yeah, it is that color. It is just a black, dusty mixture of silicate rocks, normal rock, rocky dust bits, which are left over from the formation of the solar system, and organics. Organic molecules, when they get burned by sunlight, just turn jet black. It's like a black crust on your toast. It's more or less the same thing. So it is very dark and very gray. But of course, it's also active. That's why we went there. All the pictures I've shown you, you've seen nothing happening, but the comet's actually putting out all of this material as we got close to the sun. So we had to land on the comet soon. We couldn't wait until now because we couldn't land on an active comet. So within 3 months of arrival in August last year, we had to decide on where we were going to land and get down on the surface before the comet activity built up. And that's never been done before. Nobody ever does that. You don't go and land on an object without doing a survey first. We were our own survey, so it was incredibly rush time last year. This is a picture taken by the Philae lander sitting on the side of Rosetta. That's the solar panel, the solar wing of Rosetta with a comet in the background. So it's kind of a selfie with a photobomb. Coolest photobomb in history with a comet in the background. And we had to get down onto the surface of that comet. Now, this is the place we chose to go. We looked at lots of places. You saw before it wasn't going to be easy to find a clear space. This is the 1 kilometer circle we were going to try and land in. And the analogy here is it's exactly like throwing a dart into a dartboard to scale. So if there was a dartboard right there, this is roughly the right distance for dart throwing, right? The oki to the dartboard at the end of the stage there. If the dartboard is the same size as the comet, then we were this far back. We were 22 kilometers away from a 4 kilometer object. It's the same ratio as a dartboard and where you stand. To hit the comet at all would be getting on the board. Okay, now most people on their first dart throw can do that. But we were aiming for the inner ring inside the triple, okay, the trebles. But look how much rust surface there is there, okay? So this was hard. We couldn't predict where we were going to land in that area. Now, if you're an astronaut, Ollie just said you had astronauts here last year. If you're an astronaut, it's really easy to do this, right? It's really easy. This is all you have to do to land on a comet if you're an astronaut.
Got it. Admittedly, it's translating really slow, but at least we hit our comet.
So that's Alex Gerst on the ISS, did a demonstration for us last year. He did a lot more, and you just wonder how many outtakes there were that he didn't land that earplug on the Velcro patch on the Comet. We also, and you can probably see, some of you can see at the front here, we've made a whole series of cartoons about the adventures of Rosetta and Philae. All available online. There's about 20 minutes of them, and this is a cartoon view, a brief outtake.
Philae and Rosetta were sad to be going their separate ways, but excited at the same time, because this is what they had been waiting to do. Philae was away.
In reality, of course, it's a little bit more complicated than that. We had to go into orbit at 20 kilometers, descend down to 10 kilometers, do surveys, and then drive ourselves back up to 22 kilometers, come in on a vertical dive towards the comet, and then release Philae, and then Rosetta pulled up so that we could watch Philae going down to the surface. And you have to remember that the comet rotates every 12.5 hours. And so it took 7 hours to get to the surface after that. So we couldn't even see the place we were aiming at the point when we dropped Philae off. So a lot of incredible calculations went into making all of this possible. And this is the view from Rosetta looking at Philae as Philae descended away through space down to the surface, getting smaller and smaller, so more pixelized here as it went away to the surface on this 7-hour journey. And then pictures as we actually, each of those little red circles is Philae. It's a sequence of pictures overlaid. You can see Philae moving across the surface there as it's descending down towards the surface. The gravity is incredibly weak. As I said before, you've all achieved escape velocity. We were descending at 1 meter per second towards the surface. And we've made a film here to show you from the pictures taken from the lander during the descent to show you just how slow that was. This is a descent from 60 meters down to 9. And I'm going to show the whole thing. It takes 1 minute. And I want you to, as you watch it, contemplate what you're seeing here. You're watching a primordial body left over from the birth of our solar system 4.6 billion years ago. It's roughly 300 million kilometers from Earth. It's taken us 20 years to get here. And these are the last few moments of the descent of human beings onto something that we, in some ways, are made of. Now, the last picture is taken from 9 meters above the surface because within the next 10 seconds, at 1 meter a second, we landed. So that's the last picture taken there. There was huge jubilation last year on the 12th of November. This is a control room in Germany where everybody, it was an astonishing moment to land on the comet. 20 years worth of work. And I will say, going back to the dartboard analogy, we landed in the 25. We landed 100 meters from the center of that circle. I like to keep the engineers in check. They didn't hit the bullseye. Best, we'll try again. But for a first go throwing a dart at a dartboard 300 million kilometers away, it's pretty good. So this is where we touched down. Here we go. Here are the 3 feet, the mark of Philae on the surface. And I'm going to play you now the sound of landing as transmitted through the legs of the lander in real time. This is what the landing sounded like. Now, those of you who are astute and remember the news and actually look at this picture and say, yeah, well, that's where you landed. Oh, sorry, where's the lander? Yeah, well, yes. It bounced. The harpoons, which are supposed to secure Philae to the surface, didn't fire on the day. And so even though we bounce, we hit slowly, it's a fairly hard surface. You heard that crunch. It's a layer of ice on the surface there. We hit that and we bounced. If you think back to the video you just saw, there was an angled rock or sloping surface in there. We hit that and it made us go off at an angle, fortunately, because we didn't bounce straight back up again. We flew off at an angle. And in fact, we now know that we flew for 1 hour at about 100 meters above the surface of the comet. We touched the edge of a cliff. We started tumbling, flew for another hour, and ended up in the dark spot you see down there in the circle. We don't know precisely where Philae is because this is an area with little light. Philae is pretty small. It's only 1 meter across. We haven't been able to take pictures at sufficient detail to see where the lander is. But we know it's where it is within about 20 meters or so. And at the time, Philae, because it's in this dark location, its main battery ran out as planned after 60 hours. It did a lot of science in those 60 hours, but it wasn't able to charge its secondary batteries, which were on board. It didn't have enough light through the solar panel. So Philae died at that point. But this summer, in June, Philae woke up again. Because we were closer to the sun then, it had more power in this dark place, enough to actually boot up, send signals to us, and talk to Rosetta. It's been a bad signal. It's been patchy. We've had 6 contacts, and the last one was actually in July, so it's been a while. But the reason why we haven't had a contact since then is not so much because Philae isn't working, we don't think, but we've had to retreat from the comet. Because the comet is an active body, as you see in a moment. This is where we ended up. We ended up against a cliff. Actually, some ways, this is a more interesting place to end up because it's pristine material, revealed material, not on a dusty surface where we touched down initially. So, in the intervening months, the comet's activity has been building up. This is just actually early in the spring, and we had to retreat from the comet at this point. We flew past it. Our closest approach was 6 kilometers above the surface on Valentine's Day. But since then, we've been out at hundreds of kilometers because the dust, it doesn't damage the spacecraft, but it confuses the star tracker cameras. The way we actually orient ourselves is by taking pictures of the stars. But if there's dust particles moving around, they look like stars, so we lose track. And indeed, this is what the comet now looks like from the Earth about a month or a couple of months ago, or just a couple of days before the closest approach to the sun. It was never visible to the naked eye. You couldn't have seen it, but amateurs have taken some nice pictures from the ground. Of course, we're up there studying it up close. This is the day of closest approach to the sun. As the comet rotates, we see a sudden outburst of activity there, just for 10 minutes. So as bits of the comet come into sunlight, stuff explodes from the surface and goes out, and we're there studying it. We're doing fantastic science, learning all about this amazing object, which is, again, this treasure chest to our understanding of the origins of the solar system, but the origins of human beings on this Earth as well. And so with that, I'll finish. But one thing to say, the adventure is not over, because in September next year, we do one final thing. We've got to actually, as the comet's moving back out into the solar system again, and we'd have to put the spacecraft back into hibernation. None of us want to go through that again. We don't have enough fuel, in fact, on board anymore to go around the sun another time. So in September next year, watch your TV screens, because we're going to land Rosetta on the surface as well. It's been an amazing adventure, and thank you very much for your attention. I hope you're inspired by what we've done, and you do more as well. Thank you.
Mind blown. Mind blown.
Do you have any advice for anyone in the audience who might want to go into what you do?
Be curious. You know, we do these things because they're amazing, they're difficult, they're strange, and I think if you're a curious person, and everybody in this room is, that's why you're here today, hopefully not too many people who've been dragged along by Dad who just wants to play with the Oculus, right? I'm going to play after lunch. But, you know, be curious, but also remember that when we're doing this stuff out there, there is a serious purpose to this beyond understanding our origins, the pure curiosity of science, because you know, the thing that occupies me as a scientist is that we need more people in STEM subjects. We need more people in science, technology, engineering, and mathematics, because that's the only way we're going to save the planet we actually live on. So if this stuff is inspiring to people to go and do those subjects at school, and we get young engineers, young scientists who can actually then help fix the climate and everything else we have, and do other amazing bits of science and technology, that's the ultimate reward for me. So I'd encourage everybody to just engage.
That's an amazing bit of advice. I will leave you to try and track your comets down.
Yes.
Yes,
Yes, if you will give me the comments back, that would be great. But thanks very much.
Give a huge round of applause to Mark McCaughrean and everyone at the ESA. Thank you.